All right, welcome back to Physical Organic Chemistry, CH8553. We're going to consider now the connections from page 386 in your textbook that allows us to distinguish between mechanistic possibilities on the basis of the order of the reaction and how that relates to the rate determining step. We all know that alkynes have sp hybridized carbons and therefore prefer a geometry of 180 degrees at that carbon. So if we were try to make a cyclopentine, we would have a very strained ring system. So do you think we can make it? But more importantly, how can we find evidence for it? If it's highly strained, it's going to be highly reactive. It's probably going to be difficult to detect spectroscopically, and so we're going to turn to kinetics to detect it. Folks had considered that if they took compound 1, this vinyl lithium bromide, where there's a vicinal relationship between the lithium and the bromide, they might be able to generate pentyne from this compound by elimination of lithium bromide, which could then be trapped by this cyclopentadiene. Now, cyclopentadienes, as you know, have an S-cis conformation of the diene and therefore undergo Diels-Alder reactions in a very fast and facile manner. If it underwent a Diels-Alder reaction, it would produce compound 4, illustrated here. What was also found when the reaction was actually conducted is some 2+2 cycloaddition products, or at least a net 2+2 cycloaddition product, here in illustrated in figure 3. The question, of course, now is, how did we get there? Let's consider the mechanistic possibilities. So, in our first path, path A, if lithium bromide is eliminated, lose lithium bromide, we could generate the pentyne. And this is what we would expect to be the rate determining step for this reaction. This would generate a cyclopentine which could then rapidly undergo reaction with cyclopentadiene 2, producing either the Diels-Alder adduct or the 2+2 cycloaddition. But there's an alternative pathway, pathway B, in which case the lithium bromide could react directly with the pentadiene, producing this intermediate, which we'll call 5 for simplicity, where the nucleophile here has added to the pentadiene system. Now again, this step, this bimolecular step, would be the rate determining step for this reaction. Of course, 5 can then undergo a series of reactions which would all be much faster, that involve rearrangement of the lithium and the bromide. That's a simple exchange reaction, followed by displacement to close and form the 4-membered ring, or the bromide could be at the other position. Of course, the lithium can equilibrate to the other side in an allylic type rearrangement. And of course here, if we close the ring, we make the 6-membered ring. This is the equivalent of the Diels-Alder. But what happens here? How can we make a distinction? Well, we can see that, for instance, in the rate determining step for A, we will have a rate constant for path A that produces the cyclopentine that will be dependent upon compound 1 in a first order reaction. And since that's the rate determining step, the order here will be independent of cyclopentadiene 2. In contrast, for path B, we would write a rate equation for B that involves that nucleophilic addition to the diene that would be dependent on both the concentration of lithium bromide 1 and the cyclopentadiene 2. So here, clearly, based on the order of the reaction, we could make a distinction. Well, when all is said and done and the experiments are carried out, what is found is a first-order reaction that is dependent, first order in lithium bromide compound 1, and I'm going to write it in here explicitly. For cyclopentadiene 2, it's independent of that reaction. Again, you can read more details in the inside on page 386, but this is the gist of the matter. So because the reaction is independent of the diene, and our mechanistic hypothesis that involved the rate determining step in a nucleophilic type addition, we can eliminate this as a mechanistic pathway. Now, I want you to recall how we determine mechanisms. Remember, a mechanism is our theory of how the reaction occurs. Okay? And we can never absolutely prove unequivocally a mechanism, but we can disprove them. So you see that in action here, we've disproved a bimolecular reaction, and therefore we've proven in effect the other hypothesis, that is the cyclopentine formation. Finally, what about the cyclopropane? Why is the cyclopropane there? Well, an alternative mechanism would have been to invoke radicals, but as we'll learn about later in chapter 8, cyclopropyl carbonyl radical rapidly rearranges, and so the fact that the cyclopropane ring is intact in the product is a clear indicator that radicals are not involved in this reaction.